So we would.
Okay.
So today, both Maike and Aurora will give a quick update on their work, and then Alessandro will join us later on. He told me that he couldn't make it for 4 o'clock, but he will in the meantime, and then he will give us a presentation on the warning systems in for Europe and the Mediterranean in terms of earthquakes and tsunami. So really on the observation side. Okay, let's try. Maike, are you ready? So there's a whole bunch of you. Where are you actually at the moment? Is that
I'm in Utrecht at the moment.
so you the three of you are in Utrecht. Okay, good.
Yes.
Excellent. So okay, Maike, you can start.
Oh, I cannot.
All right, please. That's my fault. Okay, you should be able to now.
Yes. Oh. Yeah, but this zoom bar is in the way.
Do you not see the button?
No.
You can navigate, you can see your mouse there.
Yeah, but on my own computer I have that zoom bar.
You can navigate with that screen.
Well, it's okay, Mike. I mean,
Wait.
yeah, I mean,
No,
it's okay to follow you on this, like, so.
Oh,
that's better. That was better. But that disappeared. Okay, good. It's not in full screen mode, but it's okay.
yeah, but wait, no. Okay, I think now. Yeah, okay, I got it. Is it okay now?
Yes, perfect.
Okay. Okay, so I will quickly remind you of the topic of my PhD, which is combining INSAR and seismothermal-mechanical models to understand earthquake sequences in complex fault systems with an application to the central Apennines. And currently I'm working on the numerical modeling part, so on the SCMs, so on the SCM models. But I've also been working on an extensive literature study so that I can build a 2D cross-sectional model in the central Apennines. And what I encountered is that there it's felt to be a slab window in the central Apennines, because in a lot of tomographic models there is a low velocity zone observed under the central Apennines, whereas you would expect a high velocity zone if there is a slab. So here on the right figure you can see a reconstruction of the slab geometry from Rapisi and collaborators. And where I want to do the cross-sectional model is somewhere in the middle of this slab window. But this complicates a 2D model quite a bit, because as you can see, this is a 3D geometry that we have to try to get into, that we have to try to capture in 2D. So what are the differences between 2D and 3D? In 2D, the slab will sink faster because it is not attached here in the northern Apennines. And in Calabria, you will just have a detached slab in your model. There is no mantle inflow in the window, which you can see here from a numerical simulation, that the mantle tries to escape from behind the slab and goes through the window. But most of this mantle inflow is in the direction of the cross section that I would do. So possibly we can impose such a mantle flow in a 2D model. And last, there will be no stress transfer of forces from the site into the cross section. So I've been running some tests with the Northern Apennines model of the Cuisto 2020 that already existed. Here is the original setup. And to start, I just detached the slab, and for the rest, I kept everything the same. Here the compositional color is just a color, all the properties are the same, so the temperature really, so only the temperature determines where the slab is. And so I will show you the result of these two models. Above is the original model, and below is the model with the detached slab. And so what we can observe is that there is no compression and substance anymore in this area because of the removal of the slab pool. There's also no extension in the outer rise, also because of the lack of slab pool. Furthermore, I observe a higher uplift rate in the origin. And in the original model, there was some mantle inflow into the lower crust, but that is not observed if you remove the slab. And last, the overriding plate seems to unbend a bit, maybe because in the top part there is compression, and in the bottom part there is extension. And so what we are left with is only the extensional earthquakes in the origin. I've been also running some other test models with different slab geometry, with a shallower slab, and I also increased the topography because in the Central Apennines the mountains are higher than in the Northern Apennines. Now I've been also trying to impose some mantle velocity as a boundary condition, and to do that I imposed a small box with a vertical velocity of 5 centimeters per year through the window, and with an increased viscosity box around it. But as you can see in this figure, which shows the horizontal velocity, the sinking of the slab increases mantle convection cells. So there's one here and one here, which are quite strong, which can be around 200 centimeters per year. So the velocity that I imposed of 5 centimeters per year is not really much compared to this strong existing mantle flow. So I've not really been able to create a mantle flow through the window. Furthermore, I decreased the density of the slab so that it sinks less fast to account for the slab attachment in Northern Apennines. So here you can see that on the left, which is the first model here, the slab sinks really fast and also creates a large amount of convection in mantle. But here on the right, I've been able to slow down the sinking of the slab significantly. So this would be something like in the Central Apennines model. I think that I still improve or start with a shallower slab because
Sorry, Mikey, I need to. I'm not sure if it's only me or if it affects everybody, but I mean your audio seems to be I mean there are a lot of interruptions in your audio.
In our meeting room. So yeah.
Okay, well, I mean, if you cannot do anything on this, I mean, we'll try to finish with this, but okay. Yeah,
okay.
it's difficult to follow you now.
Maybe I can change my
Okay, so all right, so you
Is it better now?
yeah, it might be better now. No
Okay.
more interferences so far at the moment. So okay.
Okay, so will I still want to improve with a higher slab? It starts with a higher slab because the slab is already quite deep at the start of the short-term part of the model. I also want to increase the size of the model box because especially here on the left there's a strong counterflow because the mantle reaches the left boundary of the model. And then the last slide. My computers. So I think the test results are quite promising. I can account for some 3D effects, but mantle inflow is difficult and it's not possible to impose the forces from the side. But it's also not sure how important this is. In 2D, I think I can study many things such as the interaction between the deep and surface processes, and also test if a detached slab can explain the observed surface velocities and seismicity in the central Apennines. But then there's the question if a 2D model of this 3D structure will be accepted in the scientific community, or that maybe we have to do a 3D model of which there is an option to do with a viscoelastoplastic 3D numerical model, but this will require a significant time to write a routine for the setup and also for the post-processing. So this is something we would only want to do with 2D, really wouldn't be meaningful. So I'm also wondering what are your thoughts on the 2D versus 3D model, and if you think we can capture this 3D slab geometry in 2D. And that's it.
Okay. Well, I'm not a specialist in geodynamics, so I wouldn't be able to give you my thoughts, but maybe somebody else can. Anybody for comments or questions? I have a quick one, Mikey. I'm surprised, but maybe it's because I'm not aware of this. But I mean, you have mental velocities that are, a few meters a year. That seems
Yeah.
very large to me. I don't know if that's, acceptable or.
Yeah, I was also quite surprised by this. I didn't expect it to be this high. But then, for example, when I change the density of the slab, the velocities become much lower, which I think are more realistic, maybe.
Right. Okay. Is that linked to the viscosity? I guess it is, yes. But
Yes.
okay, so maybe you can still adjust the viscosity to.
Well, the viscosity is not really imposed in the model, I think, but more calculated.
I mean, the material parameters, the base material parameters you can change.
Yeah.
But yeah, it is calculated from temperature and the like. So.
All right. Okay. All right. So you don't
Yeah,
have.
so that we can. Yeah.
Okay. I see that Menandrin wants to say something. Go ahead, Menandrin.
Thank you. Really cool update. Thanks a lot. Super interesting models. You showed these profiles with and without the slab pull, and then you said in one case you get extensional or only extensional mechanisms, and in the other case you get more versatile mechanisms. Well, what is actually observed? My recollection is that when you go over the peak topography towards the east, that you then actually get a change in mechanism. So what is the sort of the pattern that you would like to match?
Well, currently I was just changing the Northern Apennines model, so I cannot really compare to the observations there. And at the same time, the setup is also not really close to that in the Central Apennines. But I think in the Central Apennines, the observations that we have said there's only thrust faulting in the origin, and there is, only normal faulting, and there is no thrust faulting. The closest thrust faulting that occurs is quite far offshore in the Adriatic Sea. So
Okay,
yeah,
cool.
we would not
Thanks.
expect thrust faulting.
Okay, so I mean, so when you were, I mean, talking about extensional or compressional, that's really in the upper crust, yeah.
Yes.
Okay, that wasn't clear.
Any other questions or comments?
So yeah, so how will you decide about going 3D or staying in 2D?
Good question. I think I will discuss soon with my supervisors, and we will make a decision based on the test results, and if we can if we can get the good sinking velocity, and maybe if I get some better results on the imposed mantle flow, it will be possible to do a 2D model.
Okay. But I mean, in terms of I don't know, methods, I mean, the 3D model can be done. It's just a problem of time, yeah?
Yes.
Okay.
Yeah.
All right, thanks a lot, Mikey. Unless there are other questions? Nope. Okay. So we can go ahead then and see what Aurora has been up to.
Hi, everyone. Can you hear me?
Yes, we can.
I'm sharing the screen. Okay. Okay. Okay, so updates from my project, the seismic signatures of seismic processes. As you might remember, last time I presented, I showed you that I had just started with the analysis of the Amatrice catalog, and now I'm going to show you a few ideas and results that we got from this analysis. And essentially, I think that it can be divided into two big blocks. The first one is the analysis of the whole catalog, and the second block is the analysis of the clusters within the catalog. I think we do not have enough time to go through each point, so I will just focus on what we got regarding the analysis of the clusters, and especially what we obtained regarding the spatiotemporal evolution of the clusters. So first of all, we wonder why do we need to characterize the spatiotemporal evolution of seismicity. The reason why we need to do that is that we are looking for a specific pattern in seismicity which could tell us something about the potential underlying seismic processes which could drive and influence seismicity itself. And here I attached a figure from a paper that actually we discussed this morning with a group of other PhD students here in ETH. I recommend to read it. It's a science paper. It's very short and if you would like to discuss about it, I'm always open for a chat. Anyway, here they show how the seismicity density decays with distance from injection well. And from this, from the pattern that they found, they were able to understand which was the effect driving that sequence of earthquakes. In this case here, they show, for example, if the seismicity was driven by pore pressure or by pore elasticity. So this is just to tell that trying to differentiate between all possible effects that could drive seismicity is our goal. And that's why we would like to understand how seismicity evolves in space and time. And the first steps that I made regarding this matter were inspired by the works done by Ross et al. And Dandre et al. Regarding the outwards expansion of seismicity in space and time, of course, but here I'm showing two figures from their papers. And as you can see, they try to map seismicity in time by looking at the distance from the origin location of the sequence or the swarm or the cluster. And then they are able to compute an average migration velocity. But in both these two works, they look at just radial distances. So I think, and we think that we could somehow improve this characterization of seismicity in space, since we are looking at three-dimensional group of events. So it would be interesting to look at 3D pattern. And to do so, we need to develop a smart strategy to look in 3D at how seismicity evolved. Formed a principal component analysis of our clusters in the Amatrice catalog. And essentially what this analysis allows is a characterization of the size and space of the clusters in terms of their length, width, and thickness. And what it's of our interest is that by simply computing the covariance metrics of the hypocentral location of the events within a cluster, we are somehow able to rotate the coordinate system in order to look at seismicity along the length of the cluster or along the width or the thickness of the cluster. So what I have done is by, of course, windowing the events within a cluster and looking at a group of, in this case, 20 events with some overlap in my window. All these parameters can be decided, of course. I looked at how seismicity evolves and migrates in space, not only by looking at the radial distances as shown in the work by Ross et al. That I'm referring to what I've shown in 2 slides ago, but by also looking at the migration along specific direction, the principal component, of course, in the cluster, so along length, along width, and along thickness. Then, of course, we could explore different time windows and overlap, and all these parameters, I think, should adapt to the each specific cluster, or at least to their size, duration, or to the number of events in each cluster. Of course, this is still something that has to be decided. So I would, of course, your suggestions would be very welcome. And then the next step is computing the migration velocity, not more as a scalar value has been done in the work of Danre et al., but as a 3D vector, so evaluating each component of the migration velocity. And what I was wondering is in which case and in which conditions it would be possible to compute also the variation in time of migration velocity. So if you have any idea, I would be happy to discuss about it. And then, sorry, I think I will skip these 2 slides because I'm running out of time, and I wanted to present you a new work package of my PhD project. And actually, we also presented a posters a couple of weeks ago about it in Aachen at the FEAR team annual meeting. And the title of the poster was Forward Models of Deformation Fields from Shear Dislocation Sources. And the motivation behind this project within the project is trying to understand from strain data, which is, and if there is any relationship between seismic processes and seismicity before, during, and after a seismic event, a major seismic event. So with this specific study, we would like to answer the questions related to what does strain data tell us about seismic processes potentially triggering and influencing seismicity, and if it is possible by just looking at the observed and measured strain to differentiate between different contributions to the observation. And of course, I'm referring to the effect of seismic processes, poroelasticity, and seismicity. So our plans is to model the strain field, and everything comes out from this very simple formula, the Steketys formula, which show how to compute the displacement due to a dislocation caused by a unidirectional point source of magnitude f. And of course, from the displacement field, we can always evaluate the strain and stress tensors. And this simple formula, of course, can be generalized to more complex cases of double coupled forces and finite sources, rectangular finite sources, for example. And in order to do so, we are going to adopt a series of tools developed by the tool development lab of the GFZ in Potsdam. They actually implemented they developed a code, a package, which implements this analytical solution to evaluate the 3D strain and, or better, displacement, strain, and stress field. Here I'm showing an example of the output of their package. And we would like to do a similar analysis, but in Bedretto Lab, which represent a quite unique setup and a quite unique opportunity for us to have an extensive view of the strain field because of the combination of different arrays which measures strain, and because of their location. Here I'm showing, for example, the experimental volume in the case of the Walter experiments. These are all the boreholes, and the strain sensor are these gray dots. So essentially we have strain measurements, but we don't know exactly how to interpret these observations. As you can see here, this is just an example of how weird could these strain measures be. As you can see, along a single array of sensors, the strain seems to change polarity multiple times. And of course, we still do not have a model which is able to explain this behavior in the strain field. So our goal is develop a model which could explain the data that we observe, and the data that will be collected in the upcoming experiments. The first one will be in mid-April, so we want to get ready. We want to be ready to analyze the data that we are going to collect. And as first steps to develop this model, we are going to start with very simple assumption of homogeneous and elastic half space medium. We are going to assume a finite rectangular source, just a shear dislocation, and with a uniform distribution of sleep. But of course, we need to add some more complexity soon to our model and try to take into account of both, for example, the poroelastic and anisotropy of the medium. And we would also like to model more complex sources and to take into account also of the possibility of having multiple sources in different locations. And at the end, our long-term goal would be trying to perform an inversion of this data in order to retrieve the sleep distribution at the target and at secondary faults. Of course, it will take time, but this would be the goal. And having, for example, an idea of which is the source of the strain field in our experimental volume would, of course, help us understanding which is the underlying process who generated that specific deformation field. And we could also try to correlate it to seismicity and eventually driving a seismic process. So that's it for me, and I'm looking forward to listen to your questions.
Okay, thank you very much, Aurora. Questions, anybody? Menandrin. I think you're okay.
No, I'm just clapping.
Oh, you're clapping.
I've,
Okay.
I've already asked
I
my
was
question.
wondering. Yeah, right.
It'd be nice to clap after these contributions for
Right.
everybody.
Okay, a simple question maybe, Aurora. For your inversion, you mentioned you're trying to correlate this with the seismicity, but I wonder if, it would make sense to actually invert knowing the seismicity, because, it tells you something on, the strain sources, the seismic, field on top of the seismic field. So basically, if you could model, using scaling laws, the seismic, the deformation field from the seismic sources, then basically what is left is what you need to model as a seismic.
Yes, you mean that seismicity could be used as an additional constraint, right?
Yes.
Yes.
Instead of correlating, after.
Yes, of course.
Yeah.
Yes.
Okay. So, the experiment will take place, you mentioned, in April, so that's very soon.
Yeah, the M0 in mid-April after EGU.
Okay. Good. Questions, anybody?
And that's just one of a series of experiments from the next 2 years.
Okay. How long will that last, actually?
The M0?
Yeah,
1 week.
1 week. Okay.
I think 1 week.
Maybe, Aurora, you should explain to everybody what this experiment is supposed to be.
Oh, we are going to try to trigger a magnitude 0 event. That's why it is called M0. So the experiments will be I mean, the agenda can be divided into different phases. So essentially, there are going to be different injection period. And yes, we are here to monitor the seismicity, and we are going to make shifts to always have everything under control. But I'm not aware of the details, actually.
I'm sure you are not, of course. But why M0 and not M1 or M -1?
Oh, yes, because we never observed a magnitude 0 event, but of course it could happen that we trigger something larger than a magnitude 0.
Yeah, I mean, what is the size of the fault, the active part of the fault as it is now?
Oh, I'm not sure. Maybe Menandrin can help me.
Yeah, so the M0 experiment is in an array that's already existing that did not have fault activation as a purpose, but it's a geothermal reservoir, and so it has multiple structures that we activated, and some of them are several tens of meters long. We don't know which one we're going to activate. So far, the biggest one that we've triggered was -1.6.
Yeah, because several tens of meters is magnitude 1, not 0. Yeah.
Yes, and we're not ready for that. So this will have we will try to trigger an MW1 deeper in the tunnel in a new lab that we're building for the FEAR project. But that's a well-defined fault zone. The current experimental setup is is more in a distributed fraction network. And so far we had operated the pumps and everything from inside the tunnel, and that's a terrible place to be when, you know, should a bigger quake happen, it'd be quite dangerous. And now our technicians have developed a remote control system so that we can operate it from outside the tunnel. And so far we had to be really cautious and stopped as soon as seismicity ramped up a bit. We had to stop the experiment for safety reasons. But now that we can do it from outside, we can actually be a bit more bold and keep injecting with the hope and the goal that we will attain moment magnitude 0.
Excellent. Very good.
So
okay.
there should be an update in Sicily.
Right. Okay. Very
At the
good.
latest.
So, any questions from anybody? Okay, I see that Alessandro has joined us.
Yes, I'm here.
Good. Right. Good to see you.
Nice to meet you all.
Okay, so thanks a lot for accepting to give a presentation on the warning systems and monitoring systems in Europe and the Mediterranean. So I don't know how long. I mean, you've calibrated the talk.
3 hours. No, I have many things to show, but probably no, I will keep within, as you suggested, within less than 1 hour. I mean, 45 minutes, but there are several things, but I can stop anywhere. I made some blocks of things, and probably the last one can be skipped if we are a little bit late.
Okay. So what we'll do is we can interrupt you. Is that okay if there are
of
questions
course.
for more details or to clarify some point?
Yes.
So don't hesitate all to ask questions during the presentation, and then there you go, Alessandro. You can go ahead.
Yes, I can try to share my screen.
Yeah.
Okay, tell me if.
All right. Yeah. Perfect.
Is it okay? So the theme is very broad, as you can see. So I cannot speak of everything in this hour. So I will mostly concentrate on what I've been doing in the last few years about the tsunami warning systems. that are based mostly on seismic monitoring. So there is a link, of course, and I won't spend much time on the first part. I also see that you had several talks by the students, by some lecturers about seismic monitoring or seismic data. So I think you are aware of many things that I will maybe mention, but not going into much detail. So I want to start with the presentation of myself. I am a geologist. I have been at ING and INGB for the last 35 years, let's say, almost. And I've been the director of the Italian National Earthquake Center here at INGB for several years. And now from 2017, I am the responsible of the Tsunami Alert Center that I will describe later. And since last month, in February, I've been elected the chair of the NEAM TWS, which means Northeast Atlantic and Mediterranean and Connected Sea Tsunami Warning System of the UNESCO IOC, the Intergovernmental Oceanic Commission. That is one of the tsunami warning systems worldwide that I will show in a minute. And my research activity in these many years has been on earthquakes and on tsunamis. But I looked at the presentation of, I don't remember the name, I think the last one you had 1 month ago, and I saw he, of course, he rightly showed his activity in books and things like that. And so I tried to put some of my last decade, let's say, of work, and I realized that everything is all not really about earthquake research as it's normally intended, but some cross discipline, like this book that we published in 2015 that is called Earthquakes, Communications and Law, let's say. And this originated after the earthquake of L'Aquila in 2009. And for those who are not aware of this, there was a long story with the trials and convictions of seismologists, of civil protection officers, and so on, that has been discussed a lot in Italy, and not only in Italy. So I've been working on this for a few years. After that, I wrote another book. This is that was a collection of articles by the first one of seismologists, engineers, sociologists, lawyers, and journalists, and so on. This one is another one I published the year later. It's about earthquakes, but it's devoted to let's say to people, to lay people, and it's regards stories about earthquakes. It's sotto i nostri piedi means below our feet, and it's about earthquakes, scientists, and charlatans. So many stories about how earthquakes science is used, is abused, it's misunderstood, and so on. And after that, there was another book on let me just say again about science, law, and criminal trials in the risk era. The collection of papers from again by law experts and scientists, and so on. And the last thing I want to show is is about other things like science communication about earthquakes and tsunamis. That is one of my activities in the last few years. So everything you see here is not the subject of today's talk, but it's something that I want you to be aware, because we as scientists and you as scientists will probably have to deal with these arguments in your career, in your activity. I hope not as some of my colleagues as defendants or in some trials, but anyway, probably as experts, as commenters, or as scientists who participate to also to what is our role as scientists within the society. Okay, let's do it short. And so I will speak a little bit about seismic monitoring and then about tsunamis, the organization of tsunami warning systems worldwide and the Mediterranean specifically, and what we do in hazard assessment, in real-time monitoring and warning, and in mitigation if we have time. Something that you probably, some of you know, I don't know if all of you, is this document, which is something I think you should take a look at and read. It's a Sendai framework for disaster risk reduction, because it says many things. It came after the tsunami and the earthquake and tsunami in Japan in 2011, and other things, other disasters. But the important thing here is that there is an emphasis on early warning systems, but also the emphasis is, the focus is on the people-centered approach. So I go back to what I just said at the beginning. We need that people are aware of what we do to reduce the risk. They are an important part of the chain. We cannot think of doing this type of let's say applied science without having a participation of people, of local authorities, of different stakeholders, let's say. And something that is clear from this document is that the role of scientists, scientists from academy, scientists from institutes, research institutes, needs to be also not only to produce science, which is okay, to produce technology and so on, but also to share it with the society. Okay, I want to read all these things, but this is the chart of this document, which is a 15 years time frame, 2015-2030. You can read it. I will give you the presentation. You can read this, the goal, the expected outcomes. That is but I will skip all the details here. I invite you to read this document.
Just a question, Alessandro. So that's
that's
the UN framework, is that right? So I mean, does it come along with some, funding at the international, scale?
Oh, sorry, David. Can you say it again? I didn't get.
So I was wondering, that's a guideline, but I mean, is there? I mean, what are the actions? I mean, towards getting to.
Okay, well, these kinds of documents do not imply, let's say, funding to do specific things, but are documents like the one you see here, the agenda of the United Nations 2030. They indicate the way, some ways, they indicate some path to the member states, in this case, UN member states, to adopt some national indications, national regulation to do something. For instance, in the Agenda 2030, there are 17 goals. As you can see, maybe you can read read them here in some of them. These are in Spanish, but in any way, it's reduce poverty, I'll say poverty, fin de la pobreza, or very, very general themes, the environment, to protect the environment, and to make the society more just, and so on. So these are not strict, let's say, indications, but general things that have to be endorsed by the countries in their politics. It's not very effective way to do, but there is someone who let's say tracks some goals and some priorities for the next 10 or 15 years in this case, and the Sendai framework in the disaster risk reduction, or in general to improve the life on our planet. Okay, let's see. I don't know if I answered to your question.
Yes.
Okay, I think you know this thing here is it's a very nice animation with showing the earthquake activity in the last 15 years. I don't want to comment so much because I think every one of you why and which are the main active areas worldwide, but it's just to introduce the topic. This is done by the Pacific Tsunami Warning Center, and it's because, as you know, most of the earthquakes and the large earthquakes occur near plate boundaries and at sea or near the coasts, and so many of these earthquakes that you see are tsunamigenic. Now we are at 2004. You will see in Indonesia here the big the big earthquake that produced the tsunami of 2004 that caused more than 200,000 fatalities and so on. And then there will be the Japan in 2015, but I don't want to spend much time on this. This second animation is about it's almost the same. These are the 120 years of earthquakes and their tsunamis. So these are the big ones, and also again you will see that they will occur. They occur in mostly in the Pacific Ring of Fire, as it's called, or in Indonesia, or in the Mediterranean, less than the Pacific and Indian Ocean. But some of them are very strong, magnitude up to 9.6, 9.5 for the 1960 Chile earthquake, and others in all around the Pacific belt. I will stop in 1960 because it's a long one, but you can find this. This is a very important event, the one we just showed, because it's 1946. It's a one in this is 1954. These two big earthquakes in the northern part of the Pacific are important because this is the 1960 in Chile. They activated the procedure for deploying the first tsunami warning system in the Pacific. So after those big earthquakes in Alaska and the Aleutian Islands and in Kamchatka, the Pacific Tsunami Warning Center in the middle of the last century started its activities based on the Hawaii Islands. Hawaii Island, as you know, and it's here. Okay. In the middle of the Pacific, so it gets tsunamis from everywhere around, and they're very unfortunate for this. I can try to move on, but I cannot. I don't know why. Okay, so I put a few questions along the presentation just to stimulate some thoughts and some discussions by you. This is the first question: which are the factors contributing to increase or decrease the tsunami potential of an earthquake or of a region? There are several of them, and you can think about it during this presentation or later on when I will send you the PowerPoint. Just a couple of slides about, I go to my country, to Italy, the Central Mediterranean, just for a moment to show how works our national network, which is not only national, but it's extended with the seismic stations. If you see the left part of the screen, in countries nearby. And of course, when you have a network like this, you have a very high rate of seismicity recorded with very small magnitudes. In some areas, we record magnitudes close to zero, where we have very dense coverage. On the other side, the other part of the net of the screen, now our activity is the worldwide monitoring for large earthquakes. In this case, you see in this map, which is a screenshot from the software Earliest that maybe some of you may know, which is done, was designed by Anthony Lomax and Alberto Michelini. And we use this for the global monitoring. It is a good software for having quick estimates of magnitude and of locations, and that is what we need for real-time assessment of tsunami potential. Just to give some data, in an average year, we record about 16,000 earthquakes in Italy. At global scale, about 300. So in 300 more than for 5.5, which is our threshold of activation, let's say. In Italy, 16,000 means several tens of earthquakes every day, which are very useful, as you know, for mostly for scientific research, not only for let's say surveillance activity and civil protection communication when there is some large earthquakes, or when there is a long swarm of small earthquakes, and so on. Based on this data, you may do some statistics, as you probably know, to understand what's going on and to see if the probability of earthquakes in some area increase or decrease, and how much, and so on, with some statistical tools, as it's called the earthquake forecast, like operational earthquake forecasting, or some developments like that one. Okay, let's go to the tsunami warning. We started in this area in the Mediterranean in 2014. Although in the previous years there was an activity of preparation to have the fundaments of the system, because you have to have a seismic network, at least a virtual seismic network connecting different networks of seismic stations, and the monitoring of the sea level, which is done with the tide gauges. So that means stations operating along the coasts, and if there are, it's not the case of the Mediterranean, with buoys, with the deep ocean sensors for measuring the sea level in the offshore. There is a paper that we published a couple of years ago about how we do this. I can send you the file if you want. And so going again to the worldwide seismicity that I just showed before, these are the earthquakes in 10 years, I think, 2002, 2015. But these are the area in which we had in the last century, or a little bit more, 120 years, the largest earthquakes. You see that there are very high magnitude earthquakes in this table, up to 9.5, which is the already mentioned 1960 Chile earthquake, but there are several 8.5 and 9 in Russia, in Chile, and so on. And in the right column, you see that the maximum water height that was recorded, and you see that is very variable. So you have, for instance, line 4 and line 5 in which you have an 8.6 in Alaska, the one I just described, in Aleutian Island, which with a maximum water height of 42 meters. But then you have another earthquake in India with only half a meter. So there is a strong variability of maximum height, and this is due to the characteristics of the fault and of the faulting mechanism, of course, the depth and so on. Okay, this is a map by NOAA, the National Oceanic Atmospheric Administration of the United States, with the sources of these large tsunamis, of all the tsunamis that are known in this time frame. And you see here that there are different symbols for different symbols for the different sources. Most of the symbols are circles, which means tsunamis generated by earthquakes. There are a few that you can see here along the Pacific or something in the Mediterranean, and something here in Indonesia, with triangles, which means tsunamis induced by volcanoes. And also you see some squares, which are tsunamis induced by landslide. And you see there are many along the Northern Europe coast, like in Norway, which are due to collapses of coastal rocks. Well, I think I will have some more slides on this. Okay, I don't know if you can see this movie. This is an interesting movie, just for showing the mechanism that you probably already know, but it's showing the concept of subduction zone, in which you have two plates moving one respect to the other, the accumulation of stress along the fault and then the rupture with the sudden push to the water above, like this. And at this point, for gravity re-equilibrium, the water starts to move in all the directions. And what happens here is that as soon as you go towards the coastline, this is a real tsunami, the one in Japan in 2011, you see that the wave slows down, but increases its height, and then like as you see here, increases its height, and then can inundate the cities. These are some images that you probably already have seen from the Japan earthquake and tsunami in 2011. And you see there are several meters of water above the normal sea level, which go inland for several hundred meters, several kilometers in some cases, drawing everything they find. Okay, how it works, this monitoring worldwide? Starting from, I already told you that in the Pacific, the activity starts in the 20th century, around the half of the century, after the 1946 earthquake and tsunami, and especially after the Chile earthquake in 1960. The Pacific was operating so in the second half of the 20th century, but when there was the earthquake of 2004 in Indonesia, in this area here, no one gave some form of some alert to the Indian Ocean countries. So this was a magnitude 9.3, I think, earthquake, a fault long more than 1,000 kilometers from Sumatra to the islands here. and all the Indian Ocean was affected with several hours for the waves to reach India, and several hours even more to reach Eastern Africa. And there were several dead people in not only in Indonesia, most of them were there, so very close to the source, with a few tens of minutes of time to escape, but several hours for the people living on the other coast. But there was not a warning system operational at that time. It's incredible now if you think that you were in 2004 with modern networks, modern communication tools, and it was something that really shocked the community. 250,000 victims for that tsunami. So after that, the UNESCO started with the Oceanographic Commission to organize the worldwide monitoring of tsunamis, and there were 4 main areas that were designed. Also, besides the Pacific Tsunami Warning System, of course, there was the Indian Ocean Tsunami Warning System. To the right, the Caribbean, let's say, so the west coast of United States, Central America, and South America, and the NEAM TWS, which is the Mediterranean and the Northeast Atlantic. So we are operating in that area, of course. As I said, also not only earthquakes can generate tsunamis, but 80% and more, that 80% of the tsunamis worldwide are caused by earthquakes. And the important factors, of course, are the magnitude of the earthquake, the depth of the fault, and the faulting mechanism. Of course, there has to be a deep slip faulting mechanism, either normal or reverse faulting, to have an efficient propagation of energy towards the water. Although also for strike slip earthquakes, there were tsunamis generated for several reasons. You may have tsunamis generated by landslides, both submarine and subaerial, and volcanic eruptions or flank collapses, as it happened in Stromboli. You will see something later, and more recently in Anak Krakatoa in Indonesia. Depending on the focal mechanism, the first sea motion can be retreat, like it happened in 2004 for Thailandia, for instance. You see there is a very broad, dried area of retreat area of the sea in this picture, or it can be an ingression like it happened in Japan in 2011. This is something I already mentioned with the movie. The shoaling is what happens when a long wave, like a tsunami wave in deep ocean, it's a wave that is several 100 kilometers long and very small, can be very what I wrote here, I don't know, speed. Okay, it was speed, and it decreases the speed, so it slows down, and the length also shortened, and the height increases. I don't know if you can read the numbers below, but when the ocean is very deep, the speed is maybe of 700 to 800, 900 kilometers per hour. So very, very fast moving waves. And going down to a few tens of kilometers per hour, like 40 or 80, when the depth is a few meters. And also you see also the wavelength decreases a lot. So a tsunami alert center like ours in Italy, but there are others worldwide, as you have seen. Basically, we do 3 things. So we try to assess the hazard, at least the hazard of tsunamis of seismic origin, which is more let's say, easy. That's not easy, but it's easier than for other sources of to be assessed, the warning and the mitigation part. This is just to give you an idea of what a geologist or geophysicist can how one can contribute to these three areas of activity. So for the hazard assessment, of course, as for seismic hazard, also for tsunami, you have to have a knowledge of active faults, their characteristics that can be known or can be inferred, like most of them are also for seismic hazard. You assess a maximum magnitude or a recurrence time and so on. You may study the paleo tsunamis as you study paleo earthquakes, and this is a very interesting thing. Also, even if it's difficult to find tsunami deposits along the coast, it's not very easy. Of course, you have to indications from the historical documents as for earthquakes, which describe the type of inundation or retreat or the height or the timing and so on. Of course, the sample is not as rich as for earthquakes, because the tsunamis are more, of course, rare than earthquakes. You have to know very well statistics if you want to do hazard assessment, probabilistic hazard assessment. There is the need of a lot of modeling, and also post-event surveys are important after tsunamis to understand what happened in detailed in the different regions. For the tsunami warning, again, you need a lot of modeling, math, and operational capacities, of course. For the mitigation part, it's important also to involve in the studies, as we do actually, social scientists, experts in planning. There is a lot of interdisciplinarity needed, and also politics, because you have to take decisions together. So with civil protection, for instance, civil protection officers and so on. This is a map of the Euro-Mediterranean, but it's only the part of the Mediterranean catalog of tsunamis. You see there are more than 200 events. Not all of them are large events, but some of them are big, like those in Crete, in the Eastern Mediterranean, in the Messina Straits, in southern Italy, and so on.
So
most of them here, the squares are the tsunamis induced by earthquakes. So there are more than 90%. There are a few due to volcanic activities. That are the triangles in Stromboli, in Vesuvio, and in the Santorini, in the Aegean Sea, and a few landslides in France or Ligurian Sea and Greece or Turkey.
Yes, I don't know.
Okay, these are two images that they took from Indonesia, the one on the left, with a study of paleo tsunamis. So you make a trench and you try to look at the strata of the sedimentation and try to identify samples of levels of the section in which you identify what are called the tsunamis. So they're different from the classical deposition along a beach. The one on the right was taken in Sicily I think a few months ago. A colleague of mine, Paolo Marco De Martini, gave me this slide. This is the light brown level that you see is probably the tsunami of Crete of 365 after Christ. So it seems that they have dated this deposit, and it's the proof that tsunami was really big, and it reached Sicily, and with some deposition like 1 kilometer inland. This is another evidence which is debated actually, but these is in Puglia, in southern Italy. These are big limestone rocks that are brought far from the coast, like 50 or 100 meters from the coast, and they surely come from the sea, because there is not a mountain in the other part, but they propose that these are due to tsunamis, in particular a tsunami which is documented in 1743 in the southern Puglia. This is one of the blocks that are very big, tons of limestones, which are have been shifted for tens of meters inland. So these are things that are studied, are investigated to understand to what happened in the history for having a better idea of the tsunami story of a region. Okay, let's move a little bit to more technical part, not very in the big detail. This is what we do for assessing the hazard. PTHA means probabilistic tsunami hazard assessment, like the PSHA for earthquakes. And you do something which is similar. We have 2, 3, 4 slides on this. You can do it at different scales. You can do at global scale, like the map that you see on the top left. The one in the center on the top part is the NEAM tsunami hazard model published in 2018. You may map here, instead of mapping PGA or whatever for seismic shaking, let's say seismic hazard, you map, for instance, here the maximum inundation height, and this is the probability of having a maximum inundation height more than 1 meter in 50 years. And you have the probability from 0 to 1 and with the red colors. This is one of the possible representation. To do it at the local scale, which is very important if you have some high value place in the coast, in a harbor, or a power plant, or nuclear plant, or whatever, you need to do something more in detail. So you have to map better for instance, the faults at sea, and you have to have detailed bathymetric data and so on. And what you do here is consider all the sorts of tsunami events for that specific area, and with their probabilities and so on. I have a couple of slides more here. So in similar to what we do for seismic hazard, you have a model with all the possible sources of tsunamis. You have recurrence, so like a Gutenberg-Richter law for all these sources. You have to consider propagation, which is the equivalent of the ground motion prediction equations, let's say, for seismic hazard, something like that. And then you go towards the hazard curve, which is the one on the number 4, which is the probability of having a certain intensity in a given period of time. So you may have high probability events with the low intensity in the left part, or low probability high intensity, so the big tsunamis, the big earthquakes and the big tsunamis. This is a scheme showing why in a specific coastal area how you model these things. Of course, you have the uncertainty to consider in your hazard curves. which is higher as soon as you go to the large events in this case, because you have less events to make a good statistics. So you have to consider this variability and this uncertainty, especially when you use this curve, this data to for instance, as we have done in Italy, to map the inundation areas. So you have to, in this case, not we scientists, but the decision makers have to decide which is the level of safety they want to guarantee in the areas, and so they can choose a higher average return periods and higher percentiles of the distribution and so on. Again, this is something similar to the hazard seismic hazard maps. You may have probability maps or hazard maps, depending on what is your input and what is your output that you need to investigate. Okay, question number 2. Which are the ingredients that shape the PTHA compared to the seismic probabilistic hazard assessment? We know that there are, for instance, side effects that affect the hazard for earthquakes, or you have other factors, and what are those that can modify the tsunami hazard assessment? Okay, let's go to the warning part. Show again the triangles of the warning, guide, hazard, warning, and mitigation. And okay, this is just an historical event that I want to mention. In 1854, there was a large earthquake and a tsunami in Japan on the 5th of November. And this guy, this man was on the hill, and he realized that the tsunami was coming, and to avoid that the people along the beach, along the coast and the lowland could have been drawn by the tsunami, he fired some plants that were on the hill, and all the people saw that the smoke, and they escaped from the sea, and they were safe because of this intuition and this warning, let's say, that was given by this guy, Horio Hamaguchi, if I remember. And the 5th of November is now the World Tsunami Awareness Day for remembering this event. So in Japan, this was in Japan. This is again in Japan in 2011. You could think, of course, that the lesson was not learned after 160 years, but of course this event was really big. It was not expected. This is another thing we have to think of, because Japan is one of the most advanced countries in science, in tsunami science, in technology, but the 2011 event was something that surprised everyone there, and it was larger than expected, let's say, as the earthquake, the magnitude of the earthquake and the extent of the tsunami, with several tens of meters of water going inland. So what the Tsunami Alert Center does, for instance, we do a monitoring worldwide. There is about one event per day of the magnitude like 5.5 or above, which is one that activates our procedures. We don't send messages for earthquakes outside the Mediterranean. We do it internally to check the procedure, to train the people, to be ready to a real event in the Mediterranean. And for the Mediterranean, we have only, let's say, a few events per year. So that's why we do it globally, to have a continuous training and checking of the procedure. We send both to the national authority, the Civil Protection Department, and to the Tsunami National Tsunami Warning Center of the Mediterranean countries the messages when there is an earthquake, which has a potential of generating a tsunami. In Italy, what happens is that the civil protection deliver these messages automatically, so without any filter, without any check, as is done for other risks, in which you have time to think, to make an evaluation. It's sent automatically to the national system components, so the municipalities, the mayors, the prefectures, the firemen, all the agencies which have to do something in case of a tsunami. Then what we do is, after the first message, which is sent in a few minutes, with only the data from the earthquake, we don't have any idea in the first 5-10 minutes if a tsunami has been generated or not. So we we start analyzing the tide gauge data, which are not many. In the Mediterranean, there are maybe less than 100, so they're not very dense. But based on this data, we send the messages of confirmation if we see something in some of the tide gauges closer to the epicenter, let's say to the fault, or we cancel the alert after a good time. Let's say we have to wait a little bit to be sure that there is not a tsunami. So it's at least a couple of hours. Okay, this is already said. Oh, okay, these are the events that we have analyzed. We have for which we sent messages in this area from 2017. I forgot to mention, we started in 2014 in pre-operational, let's say, mode, and then in 2016 we have been excuse me, accredited as a tsunami service provider for the Mediterranean, and we started to send messages to the several countries of the area and to our civil protection. And from January 2017, we had about 40 events. Just a second. The green points, the green circles are the information messages. So it means magnitude 5.5 to 6, about 6.2, in which you don't have a real alert. It's a message of information that you send to the Tsunami Warning Center and to the civil protections to say that there has been an earthquake of magnitude 6, but you don't expect a tsunami. But anyway, you have to be careful, let's say. For orange and red, you have a local or a regional alert level. We have at the moment 2 alert levels, the orange and the red. The orange means that you expect a run-up, so a inundation of up to 1 meter's height. And red means that you expect waves more than 1 meters. More than 1 meter. How much more than 1? It's not in the procedures right now. So you have to have something that tells you how much you have to evacuate, which area you have to evacuate in case of a red alert. And as you probably will see later, we have used the probabilistic hazard assessment to define the areas. So as the highest the hazard, the largest the area that you will have to evacuate. Let's see. I will show a couple of examples to show you what happens in a case of a small or a big alert. We have a case in 2020. We had an earthquake in this area in Samos Island in Greece, close to Izmir. This earthquake was magnitude 7, and it produced several damages in the island and also in Izmir, with several collapse of building that collapsed, and the tsunami. Not a big one, but a dangerous one, as you will see later. And then I will show you this case here, this you can recognize is the big earthquake of Turkey last February. And also this was not so far from the coast not to generate a tsunami alert. And this triggered a lot of post-event evaluation that I will share with you. Okay, this is the just to give you an idea of timing. You see, this is the tsunami, the simulation of the tsunami of 365 after Christ. It's a well-documented earthquake with big damage in the Crete Island and in other islands, with the uplift of the coast of several meters, which was mapped, and with a tsunami that destroyed several towns in Greece, and it reached the North Africa, here in Libya, for instance, as you see, in about less than half an hour. You see, I stopped at 29 minutes. And also it reached the Italian coast after about 1 hour. And you see, Sicily is the one that I showed before with the trench, with an inundation of several hundred meters also in there. This one is another earthquake that we had in the last few years, if I remember well, in Zakynthos in 2018. It was a small earthquake, smaller than that, I mean 6.7, if I remember. And it also produced a very small tsunami. Fortunately, this was a strike slip mechanism, and so the tsunami you see here, we are in a scale of centimeters. It was recorded actually because the instruments recorded these long waves compared to the normal sea waves, but not more than 15, 20 centimeters. And this is the trench of the Cretan earthquake that I showed before. Okay, let's take a look at Samos. How long should I speak, David? In 10 minutes more?
Well, I mean, you mentioned looking at 2 case studies. I think that will be nice to see them. So that's the first one. And
okay,
then
I'll show you a couple of examples. Okay, this is the Samos earthquake of magnitude 7, October 30, 2020. And this is the real-time map that we produced for this earthquake. I forgot to say that there are not only our tsunami service provider in the Mediterranean, but there is one for in Greece, which is the NOAA of Athens. There is the one in Turkey, in Koeri, in Istanbul. There is one in France, in Senalt, which is in Paris, based in Paris, and another one in Portugal, in Lisbon, the IPMA. Every of these 5 tsunami service providers covers a different region, and there are some overlapping, which is one of the things that is helpful because we have several different estimates, and it's for redundancy and for checking and so on. But of course, it may generate some let's say more uncertainty if you send messages which are not identical, let's say. And this happens because you use different procedures, different networks, and so on. But anyway, going back to the Samos case, you see here in our case, we estimate this epicenter, the magnitude 7, and the red points are the ones in which you expect more than 1 meter of inundation. The yellow, orange should be orange, but it's yellow. It's the ones in which you expect a smaller tsunami, and the green, it's you don't expect a tsunami. Okay, this is the same with our software showing the different messages and so on. And this is an example of one of the tide gauges that we recorded, we analyzed after the event. You see here in the bottom part is the zoom of the event part. say you have a theoretical arrival time in the green line, and then the signal. And you see here, it's not a big one. This is not very close. It's only a few centimeters, like 10 centimeters, plus or minus. And you see there are several waves which are clear, and often the second or third waves are larger than the first one for different reasons. And if I can, I have a movie to show this, but I don't know if it's a little bit too heavy. I will try. On this webcam, it's very interesting because it shows the different phases of this tsunami. This is in the Samos Island, very close to the epicenter. I will try to show the movie here. I don't know if the network will allow to show it. Tell me if you can see it regularly. Okay, you see there is the first retreat of the sea in the area on the left top of a few tens of meters. The earthquake just happened 2-3 minutes before. The lady slowly goes away, maybe too slowly. There is a first wave coming in 2 minutes after the retreat, not very big, actually probably half a meter above the normal sea level. And then there is the retreat again. In 1-2 minutes, the lady went back, and you see there are already some boats around. And then you have this second wave 3 minutes after, which is very powerful. Although it's not a very high tsunami, like probably 2-3 meters here, not more, 2-3 meters of height, but it's very violent. It's very powerful, and you saw that it brought a lot of, carried a lot of refrigerators and things and boats and doors and so on. Then you do our colleagues in Greece and in Turkey made the post-event survey, mapping the water level along the walls, the trees, and so on. And the image on the right is just to show the movement that have been seen by drone, in this case on the harbor of Samos. Or Izmir, I don't remember now, probably Samos, with a lot of boats crashing one against the other. And this again is an interesting movie made in Japan by in a artificial tsunami pool, let's say, in which you are put in this with the ropes and the helmet, and then a tsunami of like 50 centimeters with the energy and the speed of a tsunami wave hits you, and you see that you cannot stand. Now you can see it from above, and it's very a small tsunami, let's say, but it's think of a child or of a old person or someone with disability. You can imagine the impact. In fact, in this Samos earthquake, a lady in Izmir died for the tsunami. Okay, so now just the last case, the Turkey event of last February. You know, this was a very big event, 7.8, so a long fault, like 300 kilometers. And what happened? I'm showing the next, maybe in the next slide. This is the map with you see all the points are red. It means that it's a regional, it's a basin-wide watch level alert. So that night we warned all the countries of the Mediterranean, not only Italy, France, Spain, and so on. So it was really a big event, but after we learned that it was a strike slip fault, mostly on land, and the tsunami was actually, there was a small tsunami, I will show you, but it was very localized in the first few kilometers. And so we sent the message after 8 minutes. Why it was everything was red? Because we have a very rough, very, let's say, stupid decision matrix, but which is used in many countries, at least in our NEAM tsunami warning system, in which above magnitude 7.5 you alert all the basin. So in this case, all the Mediterranean, because it was 7.8. And the epicenter was less than 100 kilometers from the coast. So that's why it was inside the, let's say, the safety region around the coast. And, you know, this is an aftershock map of the earthquake after the second earthquake of the day after, with the magnitude 7.5 on this other fault. But this fault approximately has a length of 300 kilometers, as has been reconstructed after by several data. And as you probably know, the rupture in this case was bilateral. So it ruptured from the epicenter to the northeast and to the southwest. But actually, it could have been unilateral to the southwest, let's say, going to the sea and making a tsunami, a big tsunami, more than what was produced by the earthquake as it was really. And you know that in that area there is a subduction arc, the Cyprus arc, which could have been in our first minutes of guessing, let's say, the real fault. But it was not the case, fortunately. There was a lot of media attention after this event, not only in Italy, but in many countries, because there was this broad alert in many countries. The trains were stopped, the schools, many schools who were closed, and so on. So what we did, we were already testing another method of making the forecasting, which is a probabilistic tsunami forecasting, in which the map here you see what could have been the result of this. So a very small red area you see in this gulf here of Iskenderun, and a few points, orange points here, and green everywhere. So a big difference from the the map that I showed before. This method was published couple of years ago by this paper, so we were testing it, but it was not still in operation. It's not in operation right now. It's based on a lot of pre-calculated scenarios in which sorry, you see here you have the timeline of the earthquake, you have the first estimates of magnitude and hypocenter. You don't go to the matrix, to the decision matrix that I showed before, but you have you consider what you know and what you have in your database of faulting mechanisms and tsunami models, and you can assess the probability of having a tsunami with the faults that you know. You have probabilistic distribution for every source that you are that you know or that you are in your database, and then you have as I said, a database of pre-calculated scenarios that you use to do this evaluation, and then you make the alert definition. So this is the question. It's not only a scientific question, but it's almost a philosophical or a law question. When you have a consolidated scientific technological tool which has been approved by the scientific community and by the regulatory authority, and you have an innovative improved method, but that is still, yes, with a scientific approval, but not with the complete understanding and assessment of what is its limits and so on. What you do? We are in this now in this phase of decision making, and we have this is something which is has a lot of implications, also legal implications, when you choose one or the other way. Okay, I think I can stop here. I had just a few slides showing the new developments with the offshore instruments that we are testing with cables and with the dart buoys. We are not yet there, and also the importance of having a system, a tsunami warning system in the island of Stromboli. There is one local system that we are trying to improve. And so I go to there was a tsunami actually in 2022 in December, not a big one, just 1.5 meters of peak-to-peak amplitude, but fortunately it didn't generate the tsunami on the island, on the harbor, and so on. But it triggered a lot of considerations about this type of monitoring, which is based on a very short time frame for at least for the island of Stromboli or the closest islands. So the question number 4 is what are the challenges of a tsunami warning system like this for a volcano compared to the one that I showed before that is designed for earthquakes, for the tsunamis induced by earthquakes. Okay, I will stop here because I think it's already enough for you. It's more than 1 hour, and I will be here for answering to your question if I can. And thank you.
Thanks a lot, Alessandro. That was a very good presentation. You covered a lot as well. Okay. So it's time for questions, guys. So you can just turn on your mics if you have a question and directly ask Alessandro.
I had a question. A few slides back, you mentioned when you were discussing the Turkey event and how there was the concern. I don't know if I misunderstood as you were saying it, but you said the event was within 1 kilometer from the coast, so it's in the safe zone.
No, wait. Maybe I told it not in the right way. It was the epicenter was less than 100 kilometers from the coast. It was about 90 kilometers, 95 kilometers, and the 100 kilometers is the what I call the safety zone. So it's if an earthquake is at sea or in the coast or within 100 kilometers, we treat it as a potential tsunami-genic event.
Okay. And what helps, like, what decides that 100 kilometers? Like, what decided it?
Good question. It's something that was decided in the past decade when there was the evaluation of these methods. You see in this table you have the depth. For instance, you release an alert up to 100 kilometers depth, not for deeper earthquakes. But of course, as you know, if there is an earthquake of magnitude 6.5 at 90 kilometers, you won't have a tsunami, almost surely. But it's a very, this matrix, it's let's say it's a very conservative one. So it's the original one actually 2012 like this, it was even more conservative. Then it was a little bit improved and it became like we are using now, but we know that it's very conservative. In fact, if you go to the paper I showed with the I don't have the figure here, but if you go to this figure here. There is a figure in this paper in which we show the different methods of the decision matrix and the different percentile of the probabilistic estimate. And you see that there is a repartition, a distribution of false alert, correct alert, let's say, and missed alert. And of course, you have to play with these numbers. You know that if you are more conservative, you will have a lot of, let's say, false alert like this. It's not a false one, actually. It's an overestimated, because the tsunami actually, I didn't show it, but there was a small tsunami close to the coast of Turkey. But you may decide based on that distribution, and this is what we are discussing with our civil protection in these weeks, let's say in this month, to how much you want to be conservative. If you have a probabilistic method like this, you can decide. If you have a matrix, you already, of course, decide before that. You decide how much you want to risk to be to overestimate or to underestimate, and that's why in this case we went with that kind of alerting.
Okay, thank you.
Welcome.
More questions?
I had one actually. Actually was something related with what he already told us, but my question actually goes to the decision of the governments of the civil protection. Every country just decide by themselves, or do they have a kind of common European Commission to decide what is the level of hazard they kind of set or something like that?
No, actually, we can provide a scientific product, let's say, like the model that I showed, the NIAN TH18, which is a common base. But then every country and every government has the responsibility, the duty to decide if using it, if doing a new one, if using, I don't know, general. For instance, in Italy, we used the civil protection decided to use for the inundation definition zones, to use the average return period of 2,500 years and the 84th percentile of the distribution, which is a safe choice, as in a conservative choice. When we were in Cyprus last few months ago, we made a local study of Larnaca together with people, our colleagues from Greece and Spain, and we made a local assessment of the hazard in the area, and then we showed them to the local authorities, to the civil protection of Cyprus, to the municipality of Larnaca, and so on. And they, after discussions, after showing them to all the things, after several meetings, they decided to use 5,000 years instead of 2,500 like it did. They wanted to be more safe, let's say. And so it's a decision that is it has to be a decision by each country, by each government.
Mm.
But consider that for many countries there is the model, the hazard model, but very few countries have done a mapping of the inundation areas based on that model or on other models. They don't have any almost any mapping of like this. Some have used the kind of deterministic approach. They have one earthquake, one tsunami, historical one, and they base their planning on one single event, which may be highly conservative if you take the largest one in your catalog, or even if one that don't happen yet, you may choose a magnitude 8, 9 in front of your coast, or you may be less conservative and choose something that you know, but probably it's not the maximum that you can expect. So it's difficult to make a choice. Of course, if you have a probabilistic estimate, you are more. It's more easy to decide in which part to stay with for as the safety is concerned.
Thank you.
Thank you.
Okay, anybody? I have a quick one actually, Alessandro.
Yeah.
Wondering, I mean, so there are no, you mentioned there are no system like ocean or, you know, sea bottom systems like pressure gauges that are used in the warning system. So I'm wondering, like, you know, a place like Istanbul, which, you know, has a Marmara fault going, you know, in the sea, and we expect a big earthquake there in some time ahead of us. I'm wondering, you know, are there not any specific, you know, like warning systems for, you know, such, you know, specific areas?
They have an earthquake early warning system.
Yeah.
You know, and but they don't have yet at least a sea level monitoring system offshore. As far as I know, but I'm almost sure they don't have yet. Probably they will. We are trying to do something with the Ionian Sea, for instance, with cables and dart buoys. In the Atlantic, there is a big project by the Portuguese with the cables connected to the islands and to the coast of Portugal, in which they will be able, hopefully, to improve their timing and their assessment with data from offshore. In Japan, there are many systems like this, but no. One thing interesting that may be done, probably in Istanbul, they will try to do it. We tried in the Messina Straits, for instance, which is an area in which we had a tsunami in 1908, a big one. And we have seismic stations and strong motion stations in Sicily, in Calabria. And we tried together with our colleagues in University of Naples to use an earthquake early warning approach to feed the tsunami warning system. So in that case, we are fast, but not so fast. It takes a few minutes, like 5, 6, 8 minutes to have a first estimate and the first message. With an earthquake early warning approach, you can go down to less than half a minute, let's say. And this is, of course, you risk a little bit because those estimates are not robust, are not have a higher uncertainty. Depends on the network, it depends on many things. But you are offshore, so either you have a lot of seismometers offshore, like in Japan, but we don't. Or you have a system which is not very effective in making fast estimates in, let's say, 10, 15 seconds. But we are trying. Maybe in Istanbul, they can do it as well.
All right, thanks. Okay, last question by anybody? I see it's 6 o'clock already, so okay, it's late, so I guess everybody's eager to go home. Thanks a lot, Alessandro, again.
Thanks to you. It was a pleasure.
Thanks, Alessandro.
Thanks. I'm available if you want. You have my email if you need some papers or this presentation or whatever.
Now we actually, the presentation has been recorded, so anybody can. You have a YouTube channel, so everybody will be able to, you know, revisit it if needed.
Okay.
But, again, thanks a lot for the very you know, thorough presentation of.
You're welcome. Thank you.
Systems. And okay, so that's it for today. So we'll meet again in 2 weeks' time. Well, in the meantime, I hope everybody's gonna make you know, big progress in their PhDs. Okay, bye everybody. Then.
Bye bye.
So thank you. Bye bye.
Bye bye.
Thanks.
Everybody.
Ciao.
Bye.
Bye.
Ciao,
Bye.
grazie Ale. Ciao.
Ciao Bruno, ciao Francesco.
Ciao.
Bye David. Bye everybody. Ciao.